Thanks very much, and thanks for coming today. It's been a very busy day, and a lot of people here have been there all day. Um, Thank you for hanging out. What I want to talk to you about, my name is Somak Raychaudhury. As you heard, I work at Ashoka University, but until recently, I was very much in Pune. I was part of the Inter-University Center for Astronomy and Astrophysics, where I still have a position, and IUCAA. So, and many of you would have actually come to talks that I have organized in the last few years. In my work as an astronomer, I work, and I'll tell you a little bit about the kinds of things we do, work a lot with observatories in space. And a lot of people then ask the question, why do you need to go to space? And this is why I thought I'd put together a little bit of an explanation of why we have to go to space to see the sky. And astronomers need to do that. Now, normally, one would think that what astronomers do is look at the sky and see stars. Now, that anybody can do. And in that way, astronomy is one of the oldest subjects, as it were, because people in the days when there was no internet, no streaming, no television, no film, the entertainment in the evenings after dark would be looking at the sky. And so wondering what the sky is and what those things are there in the sky was always a big subject. And then people figured out that by understanding what things there are in the sky, one can actually get a lot of things done. For example, they help in navigation. They help often people started fearing things in the sky and started thinking about whether things that they see in the sky actually are omens for danger or can cause problems. And of course, the whole subject of astrology came out of that. But all that in the thousands of years in which humans have looked up at the sky and thought about the sky has been limited to the light that our eyes can see. It so turns out that our eye does not, the naked eye does not see all the light that comes from the sky. And so, and of course, everybody sees the sky in a different way. Everybody does not see the stars as Van Gogh would have. The entire electromagnetic spectrum consists of light of different kinds. We call light, and the light is only the central part of this, which is the visible light, which our eyes pick up. But exactly the same kind of radiation can be there, which are not picked up by our eyes. So in this, we can see they're characterized by certain things that we quantify in terms of how to measure the energy of the light that comes. High energy radiation or low wavelength radiation or high frequency radiation consists of gamma rays, X-rays, ultraviolet rays. Low energy radiation could be radio, microwave, and these are long wavelength rays. And so the difference between radio, microwave, X-rays, ultraviolet, and visible light is just in the energy of the photon, the energy of the radiation. And our eyes are just sensitive to only a small part. And in history, till about 100 years ago, our knowledge about the universe was just restricted to just the amount of light that we could see with our eyes. And even after we started using telescopes, eventually through the telescopes, you actually used your eye as the detector of the radiation. So that's all we knew. And this is why, even though astronomy is the oldest science, astrophysics, which I'm going to talk about now, is one of the newest sciences. Because only recently, we've started to look outside the visible range and started to explore the other kinds of light that come from the universe. And why is that important? It is important because things look very different in different parts of the spectrum. Just look at what the sun does. The sun, when we look through a film or whatever, or a telescope and look at the sun, it looks boring. It's just a yellow disk, right? Sometimes you have a couple of spots on the sun, that's it. But look at what it looks like in the ultraviolet. That's because there are high energy storms going on the sun all the time, magnetic storms. Those big storms that you see there, some of them are the size of the Earth. And that's happening all the time. And unless you know about them, and we've only discovered them in the last 100 years, you wouldn't know what the sun is doing. What is the relation between the sun and the Earth? We wouldn't know. Look at what it looks like in the X-rays. Look at what it looks like in the radio. They're very, very different. And in order to understand the sun, and of course anything else in the sky, you have to understand what they look like in all parts of the spectrum. Just yourself, for example. I mean, here is an example where the infrared light can be used to study different parts of you. If an infrared picture is taken of a human being, you will find that it is sensitive to how hot, warm, or cold our parts of body are. We know that our hands are cooler than our forehead or head. That shows up in the infrared picture, because the infrared part of the radiation is sensitive to the temperature, to the heat that comes out of our body, right? So there are certain things that are sensitive to certain properties that normal light is not sensitive to. You can see how butterflies are very different. Same butterfly, same kind of butterfly, they look the same to your eye. In the visible, they look very different in different parts of the infrared radiation. And infrared radiation can see through that black bag and see your hand, because it's much, much warmer than the black bag that's covering you. So you can see that if you are looking at different parts of the spectrum, you can see different things. And that's why astronomers need that. An astronomer is a detective of a special kind. You see, as a scientist, I have a problem. And that is, unlike a biologist who works with a mouse, they can go into a lab, they can handle the mouse, they can change the experiment, they can bring in other mice, they can do all kinds of things. I cannot go to the star I study. I cannot go to the galaxy I study. In order to know what a galaxy is, all I have to do is to point my camera at it and receive the light that comes from it and interpret it. So that is why it is like a detective who appears at the scene of crime a month after the murder. It's all been washed up, nothing's there. Oh, then he tries to find what stains there on the walls, and then asks people who have half forgotten what happened. And they're trying to put all these clues together and try to figure out what this murder was. That's the kind of stuff we have to do. We have to get as much information as we can about an object, and then trying to piece together what this thing is. What is the sun? What is that star? What is that galaxy? How am I going to know? I cannot go there. And that is the problem of the blind people and the elephant. So if you are taking an elephant and you're touching the tail and you're touching the legs and you're touching the ear, etc., you will have a very different idea of what that elephant is, unless all of these people talk to each other and then figure out what the elephant's shape is. And this is the current problem in astronomy and astrophysics. We have now realized that in order to understand the universe, we have to look at all kinds of light that we get. And the kinds of light are ultraviolet, radio, X-rays, visual light, gamma rays, etc., and put them all together and try to understand, because each of those things is trying to tell us something. It's trying to give us a clue about the murder. It's trying to tell us something about what happened, what these things are. So for example, I mean, if you are not daunted by graphs, this tells you, for example, what the distribution of different kinds of light there is from a star according to its temperature. So you can see that our sun, whose surface temperature is about 6,000 degrees in the Kelvin scale, would have a certain temperature where the peak would be in the yellow. And you will see there are other stars which have different temperatures, like 12,000 degrees Kelvin or 3,000 degrees Kelvin. Most of their light will come out in a different part of the spectrum, right? And so it all depends, so that the color of the star is telling you what the temperature is. And if you look at the sky, even with the naked eye, you can easily pick out some stars are blue, some stars are red, some stars are yellow, and our star is yellow. And so that tells you what kind. And you can see here that the hotter an object is, the most of the light comes out at lower wavelengths, and that means higher energy, right? So just take a look at this graph, because in the next slide I'm going to ask you a question. Take a look at this graph, right? Not now, I'm going to come back to you. Take a look at this graph and just look and see what kind of stars have what temperature. Now, next question. So, no, I'll come back to that in a minute. Here's my question. What kind of celestial objects are hottest on the surface? Okay? So you have a QR code there. If you have a phone, please scan it and try to answer. I've given you 4 choices. One is a blue supergiant. These are huge stars that are blue. Huge stars that are red, a red supergiant, like Arcturus. Then you have yellow stars like the sun, or a giant planet like Jupiter. Wow, you can see how people. No, don't listen to the others. You do your own thing. I have only 2% people who think Jupiter is bright, is hottest. 4% for reds. Great, wonderful. I'm going to stop there because I think the answers are converging. We have 15% people who think red supergiants are the hottest, I mean, in terms of temperature, highest temperature, but an overwhelming 72% think that it's the blue stars. The stars like the sun, which actually seem very hot today, is about 4%, and Jupiter. Now let's go back to the, can I go back? Can I go back? Oh no, it's not finished yet. How do you stop the experiment? We have great answers. No, right, so I'm going to go back to that. Yeah. So people who, in the 72%, chose the blue supergiant, they're absolutely right. You can see in this particular graph, as I said, the higher the temperature, the bluer something is, because most of the radiation comes out of the blue part of the spectrum. Actually, young stars, stars that are newly born, are always blue because their surface temperature is 30,000 degrees, 25,000 degrees, and they cool off, and they become more and more yellow, green, and then red as they cool off. So again, just the temperature tells you about the star. But what happens is that most of the blue stars, as you can see, would have their radiation coming out in the ultraviolet part of the spectrum. And unless you actually know about the ultraviolet part, you wouldn't know much. Now, here is the crux of what I'm saying. Why is astrophysics a new subject? And this tells you how transparent is our atmosphere. It so happens our atmosphere lets through the optical part of the light, which is right in the middle of the spectrum. And isn't it a coincidence that our eyes see it? If our eyes we were like rattlesnakes, which could only see the infrared part of the spectrum, we wouldn't know that there are stars out there. There are no rattlesnake astronomers. You wouldn't know that there are. So there is a coincidence, an evolutionary coincidence, that our eyes see just the part of the light that comes through the atmosphere. But the rest of it, the X-rays, the ultraviolet, most of the infrared, and most of the radio, they're blocked by our atmosphere. And this is why we have to go to space to see them. I started by saying, why do we have to go to space to see the sky? And that is because we have to understand astronomical objects by getting as much information as possible And most of the information coming through light does not reach the Earth, right? So you can see, and here I'm going to talk about somebody who you might have heard of, an Indian who started this whole study of what the spectrum or the color of a star tells us. So the spectrum of the sun looks like this. It's got lots and lots of, it goes from all the way from ultraviolet to the X-rays to the visual part of the spectrum. But in the visual part of the spectrum, it centers around yellow, and it is most yellow because most of the light comes out in the yellow. So Meghnad Saha's work using the Saha ionization equation actually showed how the kind of light coming out in different parts of the electromagnetic spectrum, the spectrum of the star, can tell you about the nature of the star, not just the temperature of the star, but also the chemical composition of the star. This helped us understand actually what is inside the star by studying the star in different parts of the spectrum. But Meghnad Saha did a very amazing thing. He realized that a lot of the information of the stars are coming out in the ultraviolet part of the spectrum, and this ultraviolet light, he realized, is being stopped by the ozone layer, which is about 50 kilometers up. And very interestingly, we got to know about this in the 1950s. So in the 1930s, Meghnad Saha made a trip in the US, and he visited many astronomical institutions, many universities, and gave talks. And he started saying, we have to go above the ozone layer in order to study the sky. It was an Indian who did this, and this a lot of people do not know. We know this because after he died, Harlow Shapley, who is the very famous astronomer at Harvard, wrote his obituary. And in this obituary, he said, when Meghnad Saha came to Harvard, he said something that we didn't understand then, and that is that we needed a stratospheric observatory. We needed a telescope up in space in order to study what stars look like in the ultraviolet. What Meghnad Saha said in the 1930s actually turned into, in the 1990s, the Hubble Space Telescope. The Hubble Space Telescope was built by NASA on the basis of this campaign that was started by Meghnad Saha in the 1930s. India could not take that up because we didn't have the technology to actually build telescopes in space at that time. And NASA had taken it up. It was actually Martin Schwarzschild in Princeton who wrote the first report on the basis of Saha's work that we needed an observatory in space. And we owe a lot to the Hubble Space Telescope because it was the first telescope in space. And not only was that, for the Hubble Space Telescope, the sensors that were actually made for the camera that would go up in the telescope is in some form in everybody's pocket right now, the digital camera. We now have space telescopes on the other part of the spectrum, the JWST, the James Webb Space Telescope. Thank you. And the James Webb Space Telescope observes in the near infrared, which is the other side of our visible range. And what it does is, while the ultraviolet space telescope looks at hot objects, objects that are hotter than 100,000 degrees or 1,000,000 degrees, the James Webb Space Telescope looks at things that are cooler than our sun, which are 1,000 degrees or a few hundred degrees. And it is actually churning out amazing things that we haven't seen before. The same galaxies look very different in the infrared as well as in the ultraviolet. If you go to a very high energy in the X-rays, what happens is that, as you know, X-rays, like you go to a hospital and they X-ray your body, the X-rays go right through you. They're very high energy. So you have to build very different kinds of optics to actually detect these X-rays. But any object in space that is more than 10 million degrees hot emits X-rays, more X-rays than normal light. And we did not know about them at all. We did not know that there are things out there that are 10 million degrees hot till we sent X-ray detectors into space because they don't come through our atmosphere. So what do we learn? Here's an example. We have a cluster of galaxies, and on the left, you see a bunch of galaxies, And they look very boring. They're galaxies, 100,000 galaxies in there, right? But if you look in the X-rays, on the right, you see it's the same space is full of gas that is 10 million degrees hot. And this is the gas in between the galaxies. And this is the gas that did not end up in the galaxies and is just lying in the space in between the galaxies. We did not know about the intergalactic hot medium till in the 1970s and 1980s, we managed to send out X-ray telescopes in space. As part of our work in Pune, our team in Pune in IUCAA, we discovered one of the largest structures in the universe, which we call the Saraswati supercluster. And it, at that time, attracted a lot of attention. It even became a question in the last question in Kaun Banega Crorepati with Amitabh Bachchan. And so this is the largest structure in the universe that we discovered. And we turned X-ray telescopes on it. And we find that in between the galaxies, we see this very hot gas that actually tells us what is happening in the core of the Saraswati supercluster and how clusters are coming together, galaxies are coming together, and making even bigger galaxies and clusters. Without X-rays, we wouldn't have seen it. And these are pictures taken by observatories in space. And finally, I'm going to talk about ultraviolet. I'll just take 2 more minutes, because this is a space in which India leads now the world in producing telescopes. In 2015, India sent up what is known as AstroSat. An AstroSat is a satellite with 5 telescopes on board, and one of them is the best ultraviolet telescope that the world has ever produced. And the others are X-ray telescopes. And that has revolutionized a lot of astronomy. And it has given us a lot of things that we haven't seen before. And based on that technology, I showed you before that the sun looks so different in the ultraviolet than in the normal light. You know that recently we sent up Aditya L1, which is a solar observatory that's going to look at the sun 24/7. And it's entirely built in India. And the camera for it is an ultraviolet camera, because it's going to look at the sun in that kind of, this kind of image. And it was entirely built in Pune at IUCAA. It is sitting at a place which is on 1% of the distance to the sun, at a place called the first Lagrangian point, which it reached, as you know, only a few days ago. And it has now started observing. And in my final slide, I'm going to show you some of the pictures Aditya L1 is sending us back. These are our first pictures with India's ultraviolet telescope of the sun. And they're already absolutely spectacular, world-beating images from India's ultraviolet telescope. And what they're doing is essentially showing us a lot of events that are happening on an active sun. And what happens on the surface of the sun is not that far away, because a lot of the charged particles that are involved in these storms that are happening on the sun end up on the Earth. They come and actually hit the Earth. They can actually take out full satellites. They can injure satellites. They cause the aurora borealis at the pole of the Earth. All kinds of things happen. So because we live so much close to the sun and we depend on the sun, understanding what's happening on the sun is very, very important. And Aditya L1 is, for the next 5 years, going to be the best instrument to study the sun in the ultraviolet. I'll stop there and take questions. Thank you very much.
Yeah. Hello, my name is Dhruv Shetty. First off, thank you for this wonderful session. I really liked it. The question is, when you look at the night sky, I've heard like that according to the color of the stars, you know how far back you're seeing the light of it. So when you were talking about like seeing if it was a yellow sun or a red giant or a blue hypergiant or anything like that, I was getting confused. Like then, what is the difference between the two?
Right. So actually, the color of the star has nothing to do with how far away it is. It is to do with how hot it is, right? And the temperature of a star, how hot it is depends on many things. Not all stars are equal. So some stars are very big in terms of mass, some stars are small, and as you know, the light that the sun produces or the star produces happens from nuclear reactions in the middle of a star. So if a star is very massive, it can produce a lot of energy from nuclear reactions, and so it can get very hot and it can become blue. But then if it's not so massive, not so large, it doesn't produce so much heat and it can become red, right? So the temperature is small. Except for the fact that a star doesn't remain the same size all its life, right? So as long as it's producing energy, it is the same size. As soon as it runs out of its nuclear energy fuel, it starts expanding and contracting and becoming various different sizes. And this is why I use the words supergiant or giant. Sometimes stars at the end of their life can become very, very large in size, and so their temperature changes. And so it can become, a blue star can become, by becoming a very giant star, become red, right? So it's the same star, can go through a phase when, for example, the sun is now yellow, and that is because it is producing a lot of light. Now, the sun has another 5 billion years to go. So you shouldn't be afraid. I don't think you're going to be that long. But 5 billion years later, what will happen to the sun is that the sun is going to finish its fuel, and then it's going to become a huge giant star, and it'll become very, very red, right? And so, because its surface temperature is going to change. It is now 6,000 degrees, it is going to become 1,000 degrees, something like that. So what I was trying to say is, the color of the star is related to the temperature at the surface, right? And nothing else. Anything else? Anybody else?
My name is Siddharth Srinivasan. So I wanted to ask that when you're generally looking at something in space, you're getting the light energy, so it's going to take some time to travel. So if you're trying to intercept an event that is going to happen somewhere in space, so won't you get the signal a little late? So is there a solution to getting to know it prior to the event happening?
Yeah, I know. So actually, there are many more dimensions to what you're saying. First of all, what does late mean in space? Because even as you see the sun, the light takes 8.5 minutes to come to you. So you're seeing the sun as it was 8.5 minutes ago. You have no idea whether it's there now. It might have gone, right? You'll only know 8.5 minutes later whether it's there now. So that's the sun. That's only 8.5 minutes away. The nearest star is 4 light years away. So it takes that amount of, so we are looking at something, when we look at something in the sky, we are looking at it as it was many, many years ago. Even the nearest star we are seeing as if it was 4 years ago. And most of the stars are thousands of light years away. Most of the galaxies are millions of light years away. So when we say now, we mean then. And if we have to know what something looked like in the early stages of the universe, long, long ago, all we have to do is to look very far away. Because when we look very far away, light is taking so long to come to us, we are actually seeing the past of the universe. So we have a time machine there. So I'm not bothered that it takes time for us to detect photons. Because already the photon, the light that I'm getting, is many million years old, hundreds of millions of years old. You see what I mean? Now, once it gets to you, then all the light that comes from that object then comes one after the other. So we can detect the change in light from something. So there are things called transients which change in light. For example, they go bright or dim, and they can happen over the matter of seconds. And that is not a problem because the technology we are using to gather that light has, that delay does not change, right? Yeah? Now, if you then ask me how long did it take for some light to come to you, that you can measure. by measuring, trying to measure how far away something is. So you know how long the light has come to you. Okay, so it's very different from making measurements in the lab. This is a very different way of looking at detection.
Hi, my name is Varun Deshpande, and I want to ask that light loses energy while it travels, right? So, for detecting galaxies or planets that are thousands of light years away, so can we use gamma rays, means telescopes that can detect gamma rays because they have a lot of energy, so they may not lose all of its energy.
Very good point. That very good point is absolutely right. Now, the thing is, it all depends on who emits what. As I told you, normal stars emit normal light. Sun doesn't emit that much gamma rays, for example. Gamma rays are emitted by the neighborhoods of black holes or binary stars that have neutron stars or black holes in it and things like that. Very high energy phenomena emit gamma rays. Detection of gamma rays is its own problem because if you want to detect an X-ray or a gamma ray, you have to build your detector so that it can actually detect those things. No, I mean, as you know, X-rays go right through you. So you have to build a set of mirrors and detectors which will capture that X-rays and gamma rays. And that kind of technology was developed by the particle physicists in CERN, and now we use them in astronomy, and that's very new technology. And just by the nature of how much energy is emitted by something, gamma rays, because they are very high energy photons, the number of photons that we can actually detect is very small. Because the same amount of energy coming out in gamma rays, the number of photons. So you will get very few events. So you're absolutely right. If something is so bright and is turning out a lot of energy in gamma rays, those are the best things to detect, no doubt. But most of the things in the universe don't emit gamma rays. So then, you're stuck.
Hello, sir.
Yes.
My name is Shravi Karanskar. Could you please brief me on the dark matter that is present in the universe?
Right. So I did not talk about it in here, of course, and then it's not that relevant. I can talk to you later if you want. Yes. But yes, what so happens that the universe is made up of a lot of matter that is dark, that does not emit any light at all. I talked about only things that we can see through light. And that is why I had this whole talk about seeing in other parts of the spectrum. Now, actually, most of the matter in the universe does not emit light, but it's there. But what it does is, because it is matter, it actually has gravity. And so it pulls things, and as a result, gives rise to phenomena that we can detect. So the dark matter in spiral galaxies, for example, actually causes the stars to move much faster than they would if there is no dark matter. So by looking at by measuring the speeds of stars, we can figure out how much matter there is, how much light matter, and how much dark matter. So in that way, in those centers of clusters I showed you, where the X-rays show you so much presence of hot gas, it turns out it's the dark matter in between the galaxies that is making them so hot through their gravitational energy. So actually we can measure the presence of dark matter by studying the X-rays, right? So we can use light that's coming from celestial objects to measure dark matter. But what is dark matter and what role it plays in the universe is a completely different subject, which I don't want to go into right now.
Hello, I'm Vivan.
Hi.
So basically, you mentioned that between galaxies, some gases exist. So I mean, how did they form? They couldn't just appear randomly.
No,
out
no,
of
not at all.
nowhere.
It's a very, 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 very good question. Now, the thing is, I don't know whether you've ever made chapatis. I make chapatis all the time. And I take a lot of flour, I put them on my kitchen counter, and then I put some water in it, I make dough, and then I pat it, and then roll it. And then after I make the chapatis, I look at my kitchen, and there's a huge amount of flour everywhere. On the counter, on the floor, everywhere. Not all the flour I take out of my bag goes into those chapatis. The universe has a lot of hydrogen. It was formed with a lot of energy, and that as the universe cooled, the energy, part of that energy got transferred into hydrogen and a little bit of helium. And from the little bit of helium and hydrogen that came in the early universe, the earliest galaxies and stars were formed. But not all that hydrogen got into those galaxies. So all that stuff that you see in between the galaxies is all the leftover stuff. It's a very messy business. Part of the hydrogen went into the stars and the galaxies, but most of it did not. But then how would you detect them? They are not emitting light because they did not ignite nuclear reactions in the middle, which make stars visible to us, right? You can see them because in between these galaxies, as the galaxies move very fast, they get that kinetic energy and they actually become very hot and they glow. And they glow sometimes in X-rays, sometimes in ultraviolet, and that is what we can detect them from. So it's the leftover stuff.
How do you determine how many light years away a celestial body is?
Right. That's a good point. I mean, it's one of the very fundamental problems in astronomy. It's a very fundamental thing because think of the sun and the moon. The sun and the moon, it turns out, they're exactly the same size. They're half a degree on the sky. And if you thought that things that are on the sky, the same size, they're the same thing, then you would think the sun and the moon are the same thing. But the sun is 800 times bigger than the moon because the sun is 800 times further away from the sun, from the moon, the sun is. So knowing distances is very important for us to figure out what the objects actually are, how big things are. And you might be surprised to know that till the 1930s, we did not know how large our universe is. In fact, there was a big debate going on that the universe is made up of stars and the whole universe is a galaxy. And that is because people didn't know how far away those stars are, right? 1930, less than 100 years ago. And then people started figuring out ways of measuring distances to things. This is a whole subject of its own, and I'm not going to try to explain how things are, but what happens is, I'll give you an example of how you measure the distance to the nearby objects. Okay, bear with me for 1 minute. Put up your thumb in front of your eye. Now close one eye, open it, close the other one. Do you see it move? Put that thing just in front of your face and do it again. Do you see it move much more? This is known as parallax. The further away something is, between two of your eyes, it moves less and less and less. The Earth goes around the sun. You see the star in June, and then you see the star in December. The nearby stars, you would see moving in the sky a lot more than the faraway stars. This is one of the most important ways of measuring distance to a star. You can't do it very, very, very far because soon it's going to be the motion due to the Earth's motion around the sun, the displacement of the star during the year is going to be less and less and almost immeasurable. Now we have a satellite out in space that is measuring the distance of each star, and it's measured the distance of almost 20% of all the stars in our galaxy by doing this, by doing an orbit, a very large orbit, and measuring where they see the star, from what angle, right, and measuring their parallax. Satellite called Gaia. If you actually are very interested in this, Google Gaia and you will see how Gaia works. So that's just one example. There are many, many such examples now of measuring distances, but it's one of the fundamental problems in astronomy.
Hello, sir.
Yes.
Me, Pradnya Joshi. So sorry, my English is not good, so मी मराठीतच बोलते आणि वेळ कमी.
Can you speak in Hindi? That's better for me.
Yes, yes. So I will try, and if I don't.
Tick.
I am a mother of 12th student and also a teacher in Huzurpaga High School. And my students are very much interested in this astronomy subject, but they don't know they don't know how to proceed in this science field, like what to do after 12th, how to whom we should approach, what to do. So can you help us in this?
Absolutely. I mean, if you come to me after this talk, I can put you in touch with people. You are very lucky that you are in this region, because one of the best outreach programs for school students in astronomy is done by IUCAA which is in Pune, which I used to work for and I still am part of. IUCAA has had an outreach program for schools since 1995. And we have very good programs where kids can be brought in and they can be told about all kinds of astronomy and also careers in astronomy. I'll put you in touch with the right people.
Hello.
Yes.
Actually, by late Chatelier's principle, the energy of universe tends to minimize, and all our universe is going to expand and expand and expand and expand. So at the end, the nothing will exist. Like, is there some other phenomena that will happen and some matter will be created? Like,
Yeah,
or
you're
nothing,
asking a
like
question that's very difficult for me to know on the answer to. In fact, I don't know who will know the answer to this. It is true that the universe is expanding, and it is also true, and of course you're asking a question which I did not talk about today, so I'm not going to go into in a big detail, but it is true that not only the universe is expanding, but the universe is expanding, it's accelerating, it's going faster and faster. So it's going to be a very, very big space. And as something expands, like the universe, its energy doesn't go down, but its temperature goes down. The energy is conserved, as you know. Energy remains exactly the same. The temperature goes down, and it's going to become a colder and colder place, and all the galaxies are going to be further and further away from each other. And so it's going to become a very lonely and boring place. That's all we know. Now, what is going to happen later on, and whether something will happen and bring it all back together, is linked to the question, where did it come from in the first place? Why did the universe start when it decided to start? These are questions we don't know the answer to. Astronomy, astrophysics is a very, very young subject. It only started like in the 1950s, I would say, right? And I'm amazed at what we know now in a few years. The questions you're asking are more philosophical and very speculative, and also requires us to understand the basic physics in extreme conditions. This is all for you. Maybe you'll answer this question.
Can you explain us particle accelerators and also about supernovas?
My goodness. Again, can you please stick to the talk I gave today? Because if I start answering questions on all physics, then it is going to take a long time. So particle accelerators is completely outside the area of what I talked about. Supernovae are important, but supernova is something that's related to what I said today. When stars evolve, when stars go to a stage where they've stopped making energy in the middle, the equilibrium they have, which is the relation between the energy going out and then the gravity, keeping the star together, is disturbed, and as a result, the star explodes. Not all stars do. More massive stars explode. Other stars just collapse and become very compact stars. Our sun, for example, is not going to explode. It's going to just it's going to be very big and then come back together to form something called a white dwarf. Stars that are more than about 3 to 4 times the mass of the sun, they all will explode. And when they explode, they will be spectacular because a lot of energy will come out, big fireworks, and these are called supernovae, right? We've seen such examples in our galaxy, not as many as we expect to see, but even in our lifetime, 1987, for example, there was a supernova in a nearby galaxy. Not much has happened in our neighborhood yet. But these supernovae produce some of these amazing high-energy events that produce a lot of ultraviolet and X-rays, and these can be seen by the telescopes I was talking about in space.
We have time for just a couple of questions quickly.
Okay, quick.
My question is based on this image. So as we see this ultraviolet image, and in previous slide you also showed that there are some X-ray images are there. So my question is like from the optical telescope we see we directly collect the light on the CCD. So these images are in ultraviolet X-rays. So actually from the eye or optical telescope we cannot see. So how these images are forming?
Very interesting, and of course it will take me another lecture to tell you that.
Yes.
I actually give whole courses on optics for ultraviolet and X-rays. They have different. X-rays are focused with a different kind of optics, and ultraviolet telescopes are very similar to our own telescopes, but the detectors are different. They can't be normal CCDs. Because again, the ultraviolet photons will go right through. Yeah? So this is a completely different subject of the detection of high energy photons. And I teach whole courses on them, so I can't actually say things in half a minute. But if you are interested, there's quite a lot of literature that is publicly available. Please go and take a look. Thanks. Thank you. Last question.
I have two small queries.
Okay.
First one is, what is the expected operation life of AstroSat? And the second query is, if it has got a finite life, are there any plans to have a replacement for AstroSat?
Very good questions. See, there is something, one thing to have an official lifetime. Another thing is to have whether there is a reason for it to have an official lifetime. Okay, AstroSat's lifetime was supposed to be 5 years. It's been 9 years now, and it's going fine. Not everything is going fine. A couple of instruments have dropped out, not working. For example, in the ultraviolet telescope, one channel is not working, the other channel is working, etc., etc. So slowly we'll let it die. The Hubble Space Telescope went up in 1990. It was also supposed to be a 5-year mission, still going strong. But it is being blessed by the fact that it had 3 repair missions. Then the US shuttle was running, and the space shuttle will go out and fix things. It even changed instruments. That is not happening with any other things, right? So nominally, AstroSat can run for another 10 years, and it will be supported as long as it runs. Now, question is there a reason for it not to work? There are many ways things can go wrong. Of course, there are electronics. Your computer in your house runs after 3 years, it develops problems and things like that, so they're also computer-based. There are some telescopes in which there is some coolant that keeps the detectors cool, and that coolant runs out, or there's some fuel that lets you maneuver the observatory from time to time. It needs to turn, so it needs some fuel, and once that runs out, it runs out. That's going to happen to Aditya L1. Aditya L1 constantly requires it to move, and it's got some fuel, and so we know that after 5 years, that fuel will run out. AstroSat will, at some point, have that problem, maybe. But I'm hopeful it will run for a few more years. There is no AstroSat that is planned anymore, because this was quite a big experiment, putting 5 telescopes on board. And the people who made the X-ray telescopes in the Tata Institute have all retired. So we don't have the technology in India to make more X-ray telescopes. But the people who built the ultraviolet telescope are planning a much bigger ultraviolet telescope, almost the size of the Hubble Space Telescope. It's called INSIST, and it's now being planned. Professor Annapurni Subramaniam gave a talk here today. I don't know whether she's around. She's the director of the Indian Institute of Astrophysics in Bangalore. She's one of the leaders of that mission. And that is planned. So we'll have a much bigger ultraviolet telescope than AstroSat had. But it will be just a single telescope. It's not going to be a mixture of many. Similarly, ISRO has planned many other telescopes that will go up in space over the next 10, 20, 30 years. Just keep your eyes open. ISRO has a very ambitious plan of doing quite a lot of stuff from space.
We have time for one question, final question.
Okay.
Yeah.
Yes. Hi, I am Sarthak Bhaskar. I have the question that can we retrace the light which was formed during the Big Bang, and what should we do that we do not miss the light which is coming from the planets which has been died a billion of years or a trillion of years ago?
Right. Well, let me talk about the Big Bang. The Big Bang, all the energy that we see around us was created in the Big Bang, right? The mass that makes you comes from energy that was created in the Big Bang. The energy did not destroy, so it's there. What happened at the Big Bang is something we can't see now, because that after the Big Bang, for the first few thousand years, the universe was such a small place that the photons that were created then did not go very far, right? So they were getting absorbed by other things nearby. And only when the universe became large enough that photons could go from one part of the universe to another. So when we look back, there's a limit to the age of the universe before which we can look. And we can't go right at the beginning of the universe. It is with the discovery of gravitational waves, one thinks gravitational waves don't have that restriction. And one thinks that if we look at the right frequency, we might actually see the gravitational waves that were generated in the Big Bang. That might be possible, right? So that is an interesting idea, and one can think about how to do that. And I do not know what you mean by planets that were destroyed many billions of years ago. As I said, when we get light from a star that was a billion light years away, we get that light and we don't know whether that star is there or not. Doesn't matter to us because we detect something that has come to us, right? And so in many cases, we actually see things that are no longer there anymore. But it has just arrived at us right now, right? And so that's how we build our picture of the universe. We just picture of the universe. We know that we see nearby things in its kind of recent history. But we can only see things that are very far away as they were very, very long time ago, right? And I don't know whether that answers your question because I don't think I understood your question. Thanks very much. Thank you.
Okay, thank you. And give a round of applause to Professor Somak Raychaudhury for being so patient and